Thanks everybody for joining. My name is Corey Shipe. I'm with the North Carolina Geological Survey, and I work in the Asheville office within the Department of Environmental Quality. I want to talk about how we're using drones to think about the Sparta earthquake in Sparta, North Carolina that occurred back in August. So to start with, I'll show you a few photos of our equipment. We fly drones that are available to anybody, just a commercial unit. Ours in particular is made by DJI. This is a Mavic 2. So this is what we're flying with. It's a quadcopter, carries a single color camera, which you can see right here. It doesn't zoom, but it does produce really, really high quality images. This unit will fly for about 25 minutes on a full charge. So we often go into the field with a backpack full of batteries for a full day of flying. Our controller here, you can see that we have an iPad mini. That's what we fly with. That's how we can see what the drone is seeing, give it commands, take photos, take videos, etc. And throughout the talk, you might hear me talk about UAS. And so for those that maybe aren't familiar, UAS is an uncrewed aerial system, and that's just kind of the industry term for all of these kind of pieces of the puzzle that allow us to fly our drones and capture data. So we'll jump right into the Sparta earthquake. I want to explain really briefly what the earthquake was and what happened, and then we'll look at some maps and things. This was back in August of this year, just a couple months ago. And the earthquake was occurred on what's called a reverse fault. And so I'll just show you this real simple animation here. If you can imagine, Sparta was, prior to this earthquake, it was, you can imagine some flat ground. And at some point, early on the morning of August 8th, we had a rupture occur in the subsurface. And when an earthquake ruptures, this is happening miles beneath the ground, is where that main break occurs, that break in rock that allows that energy to get transmitted. And so simplistically, we think about this as two different, we call them blocks. And so this block model would show that this block on the right was thrust or pushed up relative to the block on the left. And that's what happened in Sparta. So when we get out there, we see, and you might have seen photos from big earthquakes in California or Alaska or something like that, where you see these big fault scarps. And that would be this ground break right here in the middle of the screen. During this rupture, you have a lot of shaking at the surface. And so the little animation has these trees going and houses going. And sure enough, we saw many examples of that in Sparta with damaged buildings, damaged roads, etc. And then what we call these terms here, the footwall and the hanging wall. So I'll talk about that a little bit later on, but we'll talk about which wall is the footwall, which is the block that really didn't move too much, versus the hanging wall, and that's the block that got thrust up during the earthquake. So now we'll look at a map of how does this look in map view, how does this look specifically in relation to the Sparta earthquake. So to begin with, if I can draw your attention to the top right map, this is a map of established seismic zones, earthquake zones that we have here in the North Carolina, Tennessee, and Virginia region. Most folks watching this are probably down in Raleigh, which is somewhere about at the scale bar here. And of course, where we're working is up in Sparta. This is the far northwest section of North Carolina. Sparta is just south of the Giles County seismic zone. That's a seismic zone in Virginia that has a lot of relatively low-level seismicity, so smaller earthquakes. A magnitude 5 is a very large earthquake for this region. It was the 4th largest earthquake in North Carolina, and it was the only magnitude 5 earthquake in North Carolina that we've ever actually gotten on records, like actually on scientific instruments. So during the earthquake, I've sketched out the Little River Fault. This is actually the fault that our group here and our colleagues were able to discover during the earthquake investigation. It was not previously known, and that is what ruptured in Sparta in August. And the simple way to think about this is the block on the south, that's that hanging wall, that's what came up, and the block on the north either went down or just roughly stayed at the same elevation. And we were able to see this when we got into the field. So this is what it looks like. Here are a few field photos. I'll just kind of go clockwise around this image here. So on the top left, we were able to get a backhoe in there and actually dig a trench. We wanted to be able to see this fault in 3 dimensions, and so we did so. And when you look at that right here, this real small, this is maybe an inch of vertical displacement, but that is the Little River Fault. That's where we're able to see that the block on the left, this hanging wall, came up in elevation, and it was thrusting over the block on the right, or the footwall. If you use these green numbers here, those different layers of sediment here, this kind of reddish green, or I'm sorry, reddish brown, and this like tan color, they would have aligned with the same materials on the right side of the fault. And so that's how we can really display visually what that displacement looked like. In some places, it's much larger. Here's another expression of the fault that was maybe something like 6 or 8 inches tall. So this will vary along the trace of the fault. So how did we incorporate GIS and drones? So these yellow boxes here, these are areas that we surveyed with our drone and we captured data. It was just as important for us to understand where did the fault rupture at the surface and where did it not, because that can tell us a lot about this type of geological hazard. So when we get the drone into the field, we're usually doing one of 2 types of flights. The images on the right here were captured during reconnaissance flights. We don't really know what we're looking at yet. Maybe we just got out to a field site and we want to do some investigating. We want to just kind of get our bearings. So we might throw the drone up in the air, go up 100, 200, 300 feet, something like that, and just fly around. We're really just watching on the iPad what we're seeing on the landscape. These 2 photos are examples of these long linear breaks in the ground slope. And that represents the Little River Fault. So that's where we got really excited when we got up in the air and we saw these images, because immediately we knew, okay, we're in the right spot. We found the Little River Fault, and we know we need to do more detailed investigation in these areas. So that allows us to do these survey flights, which is this image on the left. And this is using some software where we can program many specifications. We can tell the software where we want to fly, what area we want to cover, how many photos we want to take. We may do photos on like a spacing basis. So maybe every 10, 20, 30 feet, we're going to take a photo. There's all kinds of things that we can set as far as these pre-programmed flights. And that kind of lets us be a little bit hands-off. Once we're safely flying along this blue line, the software is taking care of most of the rest, which is nice. It gives us a really high quality data set. So we capture, in many of these instances, we'll capture hundreds, sometimes thousands of images of individual pictures that we'll get on our unit. And then we can take that back to the office and we do this processing on it. So some of the data products that we'll get on the right here, you can see just a color mosaic or an ortho mosaic. It's really just one picture that we have stitched together from, again, hundreds or in some cases thousands of individual images. But what that lets us do is then also think about this in a 3-dimensional space. So we understand what elevation these different points are to each other, and that's shown on the bottom left. This is a resulting what's called a point cloud. And this is not a picture, this is a processed data product where you have millions of pixels that are in 3-dimensional space. So an X, a Y, and a Z coordinate, and we understand where these are in space, which means we can then put them into a map product like these shaded relief maps that'll cycle through on this GIF. And if you look really closely, we actually went out there and mowed the grass along the fault to try to get a better expression of it and a better look. And you can see right in the middle of this mowed area, if you follow this with your eyes, you'll start to see that little bit of a depression across the land surface. We can do the same thing at another example location. So this image you already saw on the top left, and you can see this linear break in the ground slope across the field. And what I'm toggling here is a pre-earthquake, it's called LiDAR, a LiDAR surface. So this is a topography or elevation surface. And then I'm toggling on that elevation surface that we derived from the drone data. And you can see that prior to the earthquake, as soon as this disappears, so prior to the earthquake, it was a nice smooth surface. After the earthquake, we can see that depression in the drone data. So this allows us in really fine detail to map in 2 dimensions where this rupture occurred. And so we did this all across Sparta, trying to find as much of the fault as we could. And now we're going to bring back in that 3-dimensional data that I talked about. And so we can start to draw profiles across the ground surface and see what really changed. So in this image on the right, this is that field we were just looking at. Maybe if you squint a little funny and stand on one foot, you can follow the fault rupture here through the middle of the mode area. And now we can draw profiles across that fault and see what happened in an absolute sense. So the footwall on the right, which would be downhill, down this way, relatively similar when we compare a pre-earthquake LiDAR surface, topography surface, to a post-earthquake drone-derived elevation surface. And we can see that the footwall in most cases is pretty similar, but that hanging wall, we're looking at something like a half inch, 3/4 of an inch of displacement, and that jives really well with our direct observations in the field, where we could actually lay hands on things and take measurements. So I'll give you one more example here as this GIF cycles through. This was a developed area that we studied, and this is going between a color image and then this shaded elevation data. And again, I just need to stress that both of these products were generated from just simple color images that we captured with the drone. If I gave you the color image and asked you to map where we had a fault rupture, it might be a little challenging. You can kind of do it, but you wouldn't be super confident. When we get this three-dimensional data, it's clear as could be what we have here with these two individual strands of the fault. And you can see in some cases, it's even kind of coming through a building, which unfortunately the folks who run this tire facility, that had tires everywhere in that building, because in fact, that is exactly where the fault came through. They had a lot of damage to their buildings. Another interesting part of this is that as opposed to what we've already looked at, which are these long linear breaks of the fault, now we have these series of strands of the fault. This is what we call N-echelon fractures. And this is just a different way that the Earth accommodates stress from an earthquake. Sometimes it's really nice, linear, long, straight line breaks. Other times it's these N-echelon fractures. So just to conclude, we get a wildly different perspective when we're in the air compared to when we're on the ground. So all of these field geologists here standing along the fault, they don't understand. We can't look at the ground when we're standing on it and understand the full scale of where we really are without getting a couple 100 feet in the air. We get these results just in a couple days. We don't need to contract an airplane. We don't need to get any additional equipment or software. We're kind of set up to where with relatively low inputs, we can go out and collect these type of data. The two-dimensional mapping is great to a very fine degree. We can begin to get those offset estimates like I showed you. I think next up, we're going to focus more on full three-dimensional work where we're actually looking at an entirely three-dimensional space. And one effort to that end, I'll close on this. This is not a photo. This is actually a processed three-dimensional point cloud that we can zoom and pan and rotate and flip around and really get the full geometry of that earthquake. So this is a point cloud generated from hundreds of images. You're looking at millions of pixels that we can pull measurements on. We can export to different formats. We can share with colleagues and let them zoom around and flip around the fault. So thank you for your time. And if I have any left, I'll be glad to take some questions.
Awesome, thank you, Corey. Yeah, you have a couple questions. The first question is, so the drone collected LiDAR data as well as images. Could you describe the capabilities of that drone? How did you learn to use the drone?
Yeah, it's a fantastic question. So the drone, actually, our drone does not have a LiDAR sensor. So that's just kind of coming on board with technology is just getting there. We are just capturing imagery, but we're using something called structure from motion. If you want to look that up, structure from motion is kind of how we can develop these topography surfaces from just color images. And I see another couple questions. I'll try to run through these if I have some time. Did you find evidence of the fault in the forested location from AJ? Yes, AJ, we did. One of those photos that I showed you where there was about 6 inches of offset, that was in a forested environment. Because we're working strictly with photos, with our drone, we do not have the capacity to map this fault through the forested sections. We actually did just get some LiDAR flown actually this past weekend. So we will have that data eventually. And why can't satellite imagery be used at the initial stage and then connect the drone at the local level? So I have a little bit, Barbara, if you have any additional info, maybe type it in. I'm not tracking totally, but would be glad to answer offline. We do try to use satellite imagery sources in every case that we can. But the three-dimensional capacity of the LiDAR is kind of why we're using that as our initial starting point to then compare to that three-dimensional drone data. Okay, thanks very much.